Hey, it's Dr. Pat here. We are talking about inverses today, and let's just get a little bit of background about this. What's going on here? So with inverses, what we're playing with is this idea that when you're doing directions, so if I'm here in Seattle and I'm taking a cruise up to Juneau, and we're going to come back here. So what we have here is we have two sets of directions. One set of directions to go to Juneau. I'm going north and following along the coast. If I'm at Juneau now and I want to come back, what's the directions I do? I will do the opposite things in the opposite order. I'll go south as I hang along the coast there. And so that's the idea. So road trips or things like this, directions that you give people to get to a house or to a party or something like that. To get back, back home or back to your spot, you always do the directions in the opposite thing in the opposite order. Okay, so that's what inverses are about in one sense, is to undo something that's happened. Now, if you do a combination of two functions and their inverses, what ends up happening is you just kind of go around in this vicious cycle. You may start here, do one formula, get this output over here, and then now you do use that as your input. You can get back to where you started with. So the combination of two inverses gets you back to what you started with. It's a round trip in a way in terms of functions and math and stuff. If you're using this the diagrams here for functions, you have the function f, and it's going from the letters A to the numbers. And then we want to get back to the letter A's, you would reverse the arrows. And that's what this second diagram is showing, is I reverse the arrows. Instead of going from B to 1, I'm now going 1 back to B. So when I reverse the arrows in these diagrams, then what happens is you start to create the inverse, and it does still have to satisfy certain things of whether the inverse is a function or if we got to restrict the domain. We'll talk about that later. But the key idea right now, at the very introduction of this, is inverses basically get you back to what we started. We started with these over here, and now I am getting back to what I started with. All right, so that's kind of what I'm playing with here for inverse functions. Let me get into some more. Let's go do a graphical perspective. Okay, for graphs here, inverses, what's really happening is that whole perspective change. When we reverse the arrows, we create we're doing a switching of the x and y's. The input gets switched around. So input, output gets switched. So we're going to switch those around and do for the inverse. And what we mean by that is that we start with the point 4, 7. That means we've got an input of 4 and an output of 7. When we're doing the inverse relationship, we're standing here with the 7, and we want to go, how do we get back to that 4? And so that's what the inverse is all about. It's switching that x and y's around. We switch that. And then like the point -5, 3. If the inverse of that would be 3, -5, because we're switching the x and y's, because the first relationship got me from -5 to 3. And now if I'm standing here at 3, how do I get back? Who do I go back to? I go back to -5. So in the inverse relationship, I'm using the output of the original relationship. I'm using that as the input, and the output that we get was actually the input of the original. So that input output gets switched. And so when you look at your data points, that's exactly what's happening here, is when we have this one relationship 4, 7, the inverse would be 7, 4. The output and input gets switched, the x and y's get switched. And it creates a nice little visual for us in a way to look at, is this diagonal line y equals x is the mirror image. It's like that's where the mirror is. So if I have the original function, in this case is going to be looking like something like an exponential function, then its inverse has to be a mirror image across the line. And so that's what happens. So let me step back for a second and show that. So when we do this point right here, 4, 7, and we have this other point 7, 4, if I draw a line connecting those two, if I draw it, wait, let me draw a line that actually does a decent job of that. And so I'm starting here and then I'm ending up here at 4, 7. I'm starting at negative 5, 3. The inverse relationship would be 3, negative 5. Now, if I were to draw the diagonal line, let me get that all the way going down this direction too as well. Okay, so there's that line. Here's the line y equals x. Notice that the line connecting each of the two data points is perpendicular to the line y equals x. The distance between the data point and line y equals x is exactly the same on both sides. That's where we're getting this mirror image idea. So inverse relationships are mirror images over the line y equals x. And that's what we see here. Every point that you find right on one side of the equation, of the line, you can find going directly across, you can find it over on the other side. Every single point has its pair on the other side, as long as whoops, that's not a good one because that's not perpendicular, but that's the idea that we're getting to. It's directly clear across. Okay, so here's just some examples of what we got going, different relationships of that. Notice that if the original graph does cross the line y equals x, then its inverse will also meet you right there. So every time this graph crosses the line y equals x, the inverse relationship will meet you there. Otherwise, it's on the other side of the line y equals x. Same thing with here. And then for this one, I have it erased, but what it was originally here was the equation y equals x squared is a parabola. And here's the problem. For a parabola, it has it's a function because it passes the vertical line test, but when we want to do the inverse, we've got to make sure that the inverse also passes its vertical line test. And so to check that out, it has to pass the horizontal line test here. So if I'm starting with y equals x squared, this is a bad graph to do the inverse on because it does not pass the vertical line test. Here's why. If I told you that I had a y value 1, 2, 3, let's say 4 here, a y value 4. If I told you, hey, I've got a y value of 4, that's the point I'm thinking of. Can you tell me what the x value is of the point I'm thinking of? Okay, and let's play this game for $10. Will you bet me $10 that if I tell you, hey, I'm thinking of a point on this graph, and I'm going to even give you a hint and tell you it's got a y value of 4, will you win this game? And I'm going to say no, because I'm going to cheat. I will cheat like crazy when it's $10 on the line. And what's going to happen here is I'm going to tell you line y equals 4. You tell me this point, and I will go, no, I picked this point. And so I can do that either way. And so what the problem here is that if I tell you y equals 4, it's not conclusive enough to know which exact point. So that means we have to get rid of this. We have to get rid of part of this so that it passes the horizontal line test so that we can have an inverse. Otherwise, we have domain problems for the inverse. So what I'm going to try and get rid of now is half of it. So if I get rid of half of this, this red line passes the vertical line test. It passes the horizontal line test, meaning it's 1-to-1. So there is a restriction on who can be an inverse. It has to be 1-to-1. So with the parabola, I had to kick out half of it. You get rid of it, restrict the domain. And so now this half of the parabola will have an inverse of the blue line right here, y equals square root of x. And so that's what we're going to have to do in order to do inverses is to have a 1-to-1 function. Okay, got to restrict that. That's what the whole idea is, that you can't, because here's what's going to happen. If I were to keep this and try to draw the inverse then would look like this. It would have the second half of that. But this blue graph does not pass the vertical line test. The blue graph is not a function. And so in order to make the blue line be a function, we had to get rid of the bottom half of that blue. And in order to have the inverse work out right, we got to get rid of the left hand of that red. Now we could have done the left hand of the red graph, and then it would have given us that bottom half. and just not the top part. That would be perfectly fine. So there's no reason why I always have to do the right side. And then one last quick thing here, we got domain range issues. So just remember that even though these are both functions, okay, and this is a nice function right here because A goes to 5, B goes to 2, C goes to -1. That's looking great. We got the arrow direction. If I do the inverse of that and switch the direction of these arrows, am I still a function? That's the key point. And in this case, if we switch the directions, we would still be a function because each of these is going to only one of these. Okay, so this would be my new input. So if I'm doing the inverse, here, this becomes the new domain. And then this becomes the range of the inverse. And so because I'm switching the direction of those arrows, and that's working out good. But now what happens on this other one, the second relationship, if I were to switch the directions of the arrows, notice we're going to create a problem. And the problem is at 5. Okay, this gets new range. This is now the inverse. We're talking inverse. This is the domain of the inverse because we're switching the perspective. X and Y's get switched around. Domain and range get switched around. But now notice, who does 5 go to? Does 5 go to B or does it go to A? That's a problem. So if we were looking at the inverse relationship, this one's not working for us because 5 goes to 2 values, not just 1. So that's why we need this one-to-one in order to reduce the confusion for the inverse so that it can be a function. Okay, thanks. Have a good day. I'll see you in part 2.